welcome to a video about magnetic fields. This will just be a bit of an introduction. For some reason the images aren't showing up on the iPad, but you'll have them there on your handout. It took me ages to work out what the top one was on about. I was like, why is there a bird with like smelly feet and a smelly wing and a magnet? But then I worked it out. Maybe you've gotten it straight away, maybe you still need more time like me. So magnetic fields are associated with moving charges, such as charges in an electric current. Current carrying conductors produce magnetic fields. These fields are utilised in solenoids. Magnetic field lines can be used to represent the magnetic field, and the direction of the magnetic field depends on the direction of the moving charge that is producing the magnetic field. The direction and number of magnetic field lines per unit area represent the direction and magnitude of the magnetic field, and in Stage 2 physics you'll need to be able to sketch and or interpret the magnetic field lines produced by an electric current flowing through a straight conductor, a loop, and a solenoid. And a solenoid is a collection of loops next to each other that a current might flow through. So we'll learn more about those. I'm just going to give a bit of an overview of magnets. Some of this stuff might be familiar, some of it might be new. Magnets always have a north pole and a south pole, so they're called dipoles. If you were to chop a magnet in half, just so you've got like a bar magnet, the bit that you chop, if that was the south pole and you've cut the south pole off, the end of the new chopped magnet will form the south pole. So you can't just isolate a pole, they've always got a north pole and a south pole. Like poles repel, so similarly or similar to like charges repel, like poles repel, unlike poles attract. So on our picture here, the north poles here are repelling. If one of these magnets was turned around and there was a south pole close to the north pole, they would be attracting. Magnets, if they're free to move, will align in a north-south direction. And this is how compasses work. So the compasses, or the compass north ends, point approximately to the geographic north pole of the Earth. The geographic north pole and magnetic north pole is at the, south pole of an imaginary magnet that runs through the middle of the Earth here. So north poles are up here. Vice versa, south poles are down here, down at the imaginary north end of this fictitious magnet running through the Earth. The magnetic poles and the geographic poles aren't in the exact same location. In fact, the magnetic poles are moving around, I think, 52 k's or thereabouts per year away from the geographic north pole. Every 100,000 years or so they flip, and measurements have also been showing that the Earth's magnetic field is weakening, so a flip could potentially occur soon, but soon in the grand scheme of 100,000 years. It could be in our lifetime, it might not be in our lifetime, but we shall see. Little was known about the cause of magnetism until the 1820s, when Hans Christian Ørsted, who was a Danish physicist, noticed a compass needle being deflected by an electric current. This led to the hypothesis that magnetism is a property of moving charges. So, for example, the moving charges in magnets, the moving charges in electric currents, and these moving charges produce magnetic fields in the surrounding space. So some quick conventions. Magnetic fields are represented with the symbol B. The field lines of magnetic fields run from north to south. So like the field lines run from positive to negative in an electric field, they run from north to south in a magnetic field. Field lines represent the magnitude and the direction of the field at any point. So the magnitude is indicated by field lines that are close or further apart. So when they're closer together and they're more concentrated in a particular area, the field is stronger. The direction of the field is tangential to the field lines, so tangential to whatever point the line is pointing in at the specific point that you're talking about. Field lines don't cross, as there is only one direction at any point. If the lines were to cross, it would mean that there'd be multiple directions, but that isn't the case. So same as electric field lines don't cross, magnetic field lines don't cross. So just coming back to the direction being tangential to field lines, at whatever point along these field lines, the northern end or the north end of the compass needle will point along this particular tangential direction, and it will point, I guess, towards the south, or how the field line's trajectory towards the south end of the magnet is. This image here shows that. So we've got little compasses all along these magnetic, I guess, field lines, and the compass is pointing along this line at each step of the way. This magnet is sitting on some iron filings, and they arrange themselves along the magnetic field line, so you can kind of have a tangible picture, I suppose, of what those lines are doing. So moving along to current carrying conductors, an electric current, which is represented by I, is a flow of electric charge through a conductor. It's a vector, and it's often represented by dots or crosses. So if you see a dot, it means that the current is pointing out of the page. So you have to imagine that it's like a wire that's been, like it's a cross section of a wire, and the current is coming towards you. So out of the page, a dot means out of the page towards you. If you see an X, that means that the current is travelling away from you, so into the page along a wire that's been chopped in half, or a wire that you're like looking at the cross section of. The electric current produces a magnetic field around this conductor, and on this slide, this is the rule that you use to work out which direction the magnetic field is in. So which direction. This is the right-hand rule, and the way that you use it is you point your thumb in the direction of the current along a wire, and the way that your fingers would wrap around the wire indicate the direction of the magnetic field. So you can see in this image here, current is in this direction, so this person's thumb is in that direction, and the way that their hands are gripping the wire is the direction that the magnetic field is in. This applies for straight and looped conductors. So with straight conductors, it's obviously, hopefully it's not too complicated to wrap your head around. It's not that complicated for looped conductors either, but with looped conductors it means that all of the current will be pointing in one direction inside the loop, and it will all be pointing in the other direction outside the loop. So we'll have a look at that now. So we've got a straight conductor here, a looped conductor here, and a solenoid, which is a series of loops here. I think the best thing to do might just be to look at these images. So all these looped conductors, they're all the same. I just got a few different versions, I suppose. So you could see like some of the different notation. So we've got the crosses and the dots here. So all the crosses are pointing, or the current is going into the page, or the dots, the current is coming out of the page. But these are all essentially representing the same thing. I think maybe the best thing to do would be to just have a look at these images, point your thumb in the direction that the current is going, so where you've got the eye and the arrow, or the red arrow, and then just kind of wrap your head around the way that the magnetic field is, or the direction of the magnetic field based on how your fingers would grasp the wire if they were to do that. With a solenoid, it's kind of like, so it's a collection of loops, and what happens is when you put a bunch of these together is that you can sort of generate your own electromagnet, because you've got the same like field, magnetic field, or you've generated the same magnetic field as you would have with a bar magnet. So maybe if you want to look at your notes or your handout and have a look at the magnetic field lines of this one compared to the magnetic field lines of a bar magnet. So essentially all you need to be able to do is sketch and interpret these magnetic field lines for these different types of current carrying conductors, and use the right hand rule in order to be able to do that.